Hey, Katie.
Oh, hey, Alex.
Hi.
Hey, everybody.
Hi.
Welcome back to another LiveLab. We're happy to have you here. We're going to be looking at some light today. All right, we're going to be checking out energies of light, wavelengths, that kind of stuff. So if you guys have any questions about light in general, let us know. We want to hear what you're thinking along the way. But yeah, you feeling
Excellent.
good?
Feeling great. Yeah, thanks, Katie.
Cool. I'll be helping you out whenever you need to just give me a hoot, okay?
Excellent. Will do.
All right, see you in a bit.
All right. A few weeks ago, we talked about the rainbows that we see coming off of different substances in our little tubes of gas, right? And we could see that each gas had different rainbows. Now, that depends highly on what energies they're able to absorb and re-emit back, right? So today we're going to be talking about the full spectrum of light rather than just the little sliver that we see as humans. It'll be about seeing or being able to hear an eighth of what you are actually able to hear. So we can see a very, very narrow piece of light, but most of the entire spectrum of light is completely invisible to us. Now, to demonstrate a little bit of how light works is what I have this slinky here for. This is a very absurdly large slinky, and we probably won't be using all of it. But you can think of the energies of light being related to its wavelength. Okay, whenever you talk about energies of light, you talk about its wavelength. And in particular, the inverse of the wavelength, which is the frequency. So how often the wave bobs up and down within 1 second. Okay, ooh, making a lot of noise over here. So you can clearly see that I can either make this go relatively slow or like super duper fast, right? And it should be no mystery to anyone that the faster wavelengths or the quicker frequencies are the ones that are related to higher energies of light. So we'll work our way up from the bottom of the spectrum from the lower energy light to higher energy light. And the first one I'd like to talk about is infrared light. Now, some of you guys might have heard about infrared light before. This is the stuff that you see in movies a lot that is related to like heat, because all of us are actually glowing in the infrared spectrum. Basically, the way it works is we eat a cheeseburger or something like that, and then we use that chemical energy to heat up our bodies because we're all warm-blooded, hopefully, and then we emit that energy in the form of light, so in infrared light, right? So can you guys show us the infrared light right now? Yeah? Okay. So right now you guys are seeing me in infrared spectrum. I probably look pretty funny. I imagine my nose is probably pretty cold because I can feel that. My fingers are probably pretty cold because this room is pretty cold. But then the rest of my face should be like in the reds to white areas. And that's related to the heat that's being produced there, right? Because my nose is a bit on its own out there and it's large for people, then this will cool down a lot more easily than the rest of my face, which is nice and warm. Now, I also have here, I don't know if you can see it, a cup of ice. And that should actually plummet the spectrum quite a bit, yeah? There should be like a little band on the side that tells you how hot or cold something is, and you can kind of relate it to that. Sometimes when you do this sort of thing, you can see the entire scale drop quite a bit. So like what was once like blue, like the background here, could turn like green relative to this ice, right? Because in order for us to see it through the camera, we have to associate visible colors with the colors that we can't see in the infrared spectrum, right? Excellent. I also have what used to be a warm cup of water here, and I'm not sure if this one is very visible. Yeah, this one's cooled down to about room temperature, but we can do something interesting and set out a little candle here, and maybe that'll give us a bigger heat response. more towards me. Okay. All right, so I have here a little match, and I'll light the candle just so we have a steady spot to look at. And put that up. Good. All right, can you guys see that? The little candle?
Yeah, we can.
Excellent. So that should really spike the heat of of this thing way up to the top, because these things burn at quite a high temperature.
So you're blue?
I'm blue. Oh
Yeah,
dear.
compared to the rest
Dabu
of
dee
us.
dabu die.
Yeah. So yeah, you can definitely see like the drastic change.
Amazing.
The mic isn't on.
Excellent. Yeah. So that's pretty neat. And obviously, this is useful for a whole lot of different applications. Okay. So that's infrared light. Now, infrared light is just below what we can see in the regular rainbow. In our regular rainbow, we can see things like, oh, I don't know, you can switch back to the normal view. Okay, cool. In our regular, normal, everyday light, we can see things like red light, right? So infrared means technically below red, okay? And then in there's green light, as well as purple light, and everything else that you see in your normal, everyday rainbow, or not so everyday here in California. Okay. So that part we're pretty familiar with. But then we go into the area that's just above what we can see in energy. That part is called ultraviolet. Now, we can't really replicate it, but we can peek a little bit into the ultraviolet spectrum here using one of these like cool blacklight things. Yeah, you guys may have seen these before. They basically just shine like a sweet purple light everywhere. And then things that do reflect ultraviolet light become a little bit visible to us because of the way the absorption of light works, right? In this case, what it does is it absorbs the high energy light and then reflects it or re-emits it as a lower energy light. And that way we can look into the ultraviolet spectrum. All right, so I've got a couple of things that we can play with here. I've got these little vials full of different fluids, which are pretty neat. Now this here is like tonic water. This here's, I imagine, some sort of highlighter and two more highlighters that have just been like soaked into these into this water and then absorbed. All right, so we're gonna get the studio lights here, and we're gonna look at these under the ultraviolet light, or under the black light to see into the ultraviolet spectrum. Now, hopefully, they show us up well. All right, ready? Here we go. I'm just going to scooch this until it's nice and visible. Yeah, excellent. So here you can see that this is kind of glowing under this nice purple light here. And that's not something that we normally associate with our everyday sort of light. So this lets us know that there is a part of this that glows in the ultraviolet spectrum, which is great. Now we can swap this out for a different one, because we want to look at all of these, right? This here was the tonic water. This here is one of the more common things that you have around. And this looks super cool, I think. Nice. All right, and then we have a couple more. This here is just regular highlighter fluid. Yeah, just your normal yellow highlighters. And nice. And then this next one, I think, is the purple highlighter then. Although it looks a lot like this one, right? What do you think?
There you go.
Yeah? Very cool. Now, this is good for us to know because, need to find the lights again. Woo. Okay. Because there's some creatures in our world that do get to see into the ultraviolet spectrum a little bit, and in fact, it's a large part of their life. For instance, a lot of insects, and I don't know if you can see this little guy. This here is a scorpion, technically arachnid, right? These guys glow in the ultraviolet probably so they can find each other. a little bit easier. But bees especially, they tend to see a little bit into the ultraviolet. Because when you look at flowers under this like black light, you can see like little runways for them, which is kind of neat for them to land on. So if you have like a really cool shirt or like a sweater, I don't know if you can see this under the black light, but if you wear something like that and you put on a black light, then you can see it glowing. And if you go outside with that, like on a hot summer day, then bees will just follow you around everywhere because they think you're a giant glowing flower running away from them. Yeah. Now we talked about highlighters a little bit. I want to show you guys what happens with highlighters. So I already drew something on my hand earlier, which was just out of habit, I guess. If you guys, I drew a square, okay? Because I did a little bit of a atmospheres and gases thing, and we were talking about pressure. Yeah, so I drew a square inch on my hand, but hopefully you guys can see how that turned out. Yeah, there you go. And we also wrote a nice little secret message on here in highlighter. Maybe you guys can see what it is in the light, but it's gonna show up really well when I turn on this light here. Yeah? There you go. Very cool. And I can also draw something new on my hand, just so you guys know I'm not lying about highlighters actually doing this.
You want to do this with lights off?
I'll draw it with the lights on, and then we'll turn the lights off so you can see what I draw, okay? So I'm just going to draw a little smiley face on my hand just above the square from earlier. Okay, great. Now ready? We'll hit the lights, and wha-bam! We got ourselves a smiley face. Great. All right. Sweet. So that's the ultraviolet spectrum. It's got other applications too. The higher energy light opens up a lot of doors. Now, past that in our energy spectrums is where it starts to become pretty dangerous. Now, ultraviolet light, you don't want to look at for too long with your bare eyes because it could hurt your eyes, right? And your skin as well, right? That's why you wear sunscreen when you go outside. Great. But after that, we have what is called X-rays. Now, X-rays were kind of discovered by accident, which is pretty cool. I have here a little picture of a snake. Snake. Right. Now, X-rays allow you to kind of see through the skin and the meat of the animal and just see the bones, right? Because the density of the bones allows the X-ray light to bounce off of them, while through the rest, like fleshy, meaty bit, it just kind of goes straight through.
Can you angle it towards the camera?
Oh yeah, I can definitely shift it towards the camera a little bit. Now, I'm willing to bet that everybody's had an X-ray taken of like their teeth and stuff, and you know that you're wearing like these big, heavy lead coats when you're having to take an X-ray, right? And that's to kind of prevent it from going into your your gut, because that can start causing problems. Because these lights, or this energy of light, can have enough energy to kind of knock out a piece of DNA, and then you start getting like kind of messed up cells, and that leads to cancer, right? Nobody wants that. So there you go. And yeah, immediately after like the discovery, they started working on medical applications to like see when bones are broken or when people had to be put back together, yeah?
Hold it closer to the camera.
A bit closer, there we go. So you can see this fellow here had like his shoulder repaired with a couple of screws. Goodness. Nice. And then got one more. There we go, another one. Yeah.
Bring it down a little bit.
Down. There we go, another shoulder. You can see kind of the rib cage here and then the arm going down that way. Neat. Yeah, very cool. And then beyond that, we have gamma rays, and those we definitely don't want to mess with here. But that's what you find in like a lot of these nuclear power plants and situations like that. Yeah, so that's the full spectrum, except for things like going back to the very, very beginning, we have things like radio waves and microwaves, and then come the infrareds and the visible, followed by ultraviolet, X-ray, and gamma, right? Cool. So we can just play around a little bit longer with all of this stuff. One thing I haven't showed you guys is this re-emission, right, in a different light. And a better way to visualize it is to kind of use a laser to shine through one of these vials. Again, it's going to act as ultraviolet light and then being transitioned to a lower energy state so that we can see it. Now, if we look in this piece of paper, I'm going to flip it over so that we have a clear surface. You might be able to tell that I have a purple laser here, right? Now, this purple, well, it might look blue to you just because of the way the camera is working. Now, if I take this purple laser and maybe shine it through here, you can see that it becomes yellow. But you might be saying, oh, Alex, that's because it's yellow fluid, right? It's yellow highlighter fluid. Okay, I believe you on that. But let's test it out on, not this one here. Okay, so I'm going to test it out on this one. And you can see that in here, it starts to become orange, which is really neat, right? But if we turn the lights back on, then you can see that this here is actually the purple fluid that we have, right? And not orangey at all. We can do the same thing with this one here, which hopefully shows up pretty well. So this here was the purple fluid one. Very cool. All right. Sweet. Do we have any questions yet? Or yeah.
Spencer wants to know, where are radio waves?
Where are radio waves? Right. They're kind of being beamed all around us all the time. Now, radio waves are actually on the on the scale of mountain sized. So they kind of flow all around the place. So they're very, very large wavelengths, where here we get to, on the like X-ray and gamma ray side, we get to be like super teeny tiny, even smaller than atom wavelength. But yeah, they're everywhere, and they're just being transmitted by our dear friends at the radio station, kind of all over the place.
And microwaves?
Microwaves. Yeah, okay, so microwaves work in a pretty neat way. So we have some water here, right? And when you have a microwave, basically all it's doing in the microwave is heating up water molecules. They're tuned to be exactly at the resonance frequency of water, right? So when you take a microwave and you hit water with it, then you start to like accelerate it like this, but it's resonating. So every time it gets bigger and bigger and bigger and bigger, and that means that the water molecules are accelerating, and that's what you then end up having as heat in your food that you can then eat. Wonderful and delicious. Yeah. So it's really just trying to heat up water. Now, there's some weird interactions with microwaves as well, where the resonance frequency kind of overlaps a bit with some other things. Like if you've ever, don't do this at home, but because you could really mess up your microwave. But if you've ever like put like a grape in the microwave, it bursts into a giant ball of fire because of that resonance frequency. It's actually making some plasma. It's giving it enough energy so that the electrons are completely stripped away from the molecules that make up the grape, and then that bursts into a sweet plasma cloud. Yeah, I see we have another question.
Will the violet laser make the highlighter glow?
Oh.
So it does the same thing?
We can try. It's not going to be very easy. We can try to make the highlighter glow with the purple light, I suspect that it will work. The only thing is that the light from the laser is like super high powered, right? And the spot that we're shining on is relatively small, but maybe we can get some like a bit of the side of it showing up. All right, so we're gonna hit the lights, and look at our little note here. And yeah, you can see that, I hope you can see, that the writing is showing up and kind of fluorescing under this laser here. Ooh, if I hit it directly, it's kind of crazy. I don't know if you can see that. Oof. Yeah, nice. So, yeah, problems solved. We got it.
Why is it called a blacklight if it's not actually black?
Yeah, it's a bit of a misnomer. Yeah, I don't actually know. Do you know, Scott?
Yeah.
Yeah, we're just switching out microphones so Scott can tell us.
Yeah,
why it's
so
called a blacklight.
when we're looking at this ultraviolet flashlight, it's not actually ultraviolet, like not the whole thing, right? Because
Right.
if it was only ultraviolet light, then we wouldn't be able to see it because our eyes can't see ultraviolet. So they put in a little bit of actual purple violet light just to illuminate it. Actual black lights are the ones without any of the purple in it, and they just emanate the ultraviolet.
Huh.
So that's not actually technically a black light, but colloquially we call them that.
So therefore, if you shone it, it wouldn't make a light for us. At least we wouldn't be able to see it. But
So where
Yeah.
blacklight has like the fuzziness to it when you look at it directly.
oh,
Is that
Is
my
it-
eyes? It
is
could be
it?
just
It could
my
be
eyes.
because
It's
you
me.
wear
Never
glasses
mind.
normally. That might just be that. But yeah,
You
so
can't see me behind the camera, but I just gave Katie a very weird look.
Usually-
Yes, they both looked at me like I was crazy.
usually light just travels in straight lines and doesn't make a fuzzy blob, unless it's going around like a large object, like a star or black hole. Yeah. Good questions though, guys. Sweet. Yeah. There you go. Oh yeah. We can. I've totally forgot about this bit. Okay, we can look at a little bit more on the infrared light. Okay, because it has some cool properties. One is that it has a really hard time passing through certain things, and a really easy time passing through others. Right. So I have this plastic bag. It's going to make a lot of crinkling, so I might be quiet while I'm holding this. But you might already be able to see that this thing can actually see me pretty well through the bag. And that's because this bag is colored in a way that, let's put that over here, that it absorbs the visible light for us. But the infrared light has just enough energy to pass through that object. However, on the other side of this, you can see that this plexiglass here has basically all of the visible light passing through it, but if you look at it through the infrared camera, it completely blocks the infrared light. Yeah, and this kind of leads to the greenhouse effects that you might see in the car, right? Visible light comes through here and hits the material in the car, which is probably colored in a way that it absorbs quite a bit of light. Okay, and then when that gets absorbed, it still emanates the infrared radiation or the heat that's being produced there. So that then hits the windows in your car and bounces back off, and then it's trapped in the car, and then it's like 80 degrees out, but your car is 1,000,000 degrees. Yeah. So there you go.
One of my favorite questions right now is, wait a sec, why can't I still see his beard? I think referring to the infrared camera.
Oh, can you see my beard through the infrared camera?
Well, not through the glass, but in the infrared camera, we can see that you have a beard.
Oh, interesting. Yeah, it's probably because it's very close to my face, and my face is heating up my beard, and then it still glows. It's not producing any heat on its own. Oh, here's a cool thing. Okay, but because it's attached to something, it's going to be at a similar temperature. If you ever went over thermodynamics, I think the first law of thermodynamics is something like, if object A is attached to object C and object B is attached to object C, then those three will reach thermal equilibrium. Basically saying that if a hot thing is in contact with a cold thing, then and you connect those two by like another object, then all three of those will reach some sort of equilibrium and have a certain temperature. But that's beside the point. I'm going to heat this plexiglass up with my hand, okay? Just for a moment. And then when I take my hand off of it, you'll be able to see that remaining glow from my hand being on here. So I remove my hand, and you should be able to see a nice handprint on here that'll slowly fade away as it cools back down to room temperature. It's kind of awesome. Yeah. Okay.
One question is, what does laser stand for?
What does laser stand for? Okay, get ready to write this one down. It stands for light amplified by stimulated emission of radiation. Okay, repeat after me. Light amplified by stimulated emission of radiation. It's a long, convoluted acronym for something that's relatively intuitive. It's not that intuitive. Yeah, so normally when you get light out of an atom, you excite the electron, right? And you excite the electron by giving it some energy, okay? Now, what happens with light amplified by stimulated emission of radiation is that you stimulate the electron with light, okay? So you bump it up in energy level, it hangs out there for a while, and then it hops back down, and then it releases a pair of photons instead of the one that it got originally. And that's why all your lasers are monochrome, right? Because they're all identical photons. Yeah.
I have a good question here. How do lasers remove tattoos?
I imagine you just burn the skin away. Yeah, I couldn't tell you.
It takes the ink out.
Takes the ink out? Huh. Neat. I don't know. That's yeah?
Yeah.
Neat. Yeah, or maybe it doesn't take it out or denatures it, maybe? I don't know. That's outside of my field of expertise, yeah.
I have a fun fact about the acronym laser.
Oh, yeah?
In the process of what it's doing, it's not actually amplifying anything. It's oscillating the wavelength and all those kinds of things. So the more accurate acronym for laser is LOSER, loser.
Oh.
Oh, oh. Loser? Oh, no.
Yeah, Critter says it breaks down the ink and then your body absorbs it.
Yeah.
Thank you, Critter.
Yeah, thanks, Critter. See if we got people watching out for us. When we don't know stuff, then somebody will shout it out. Excellent. I do believe we are running out of time here, but do join us next time. We have a very exciting topic. We are going to be talking about the fabric of space and time, gravity, and Einstein, and special relativity? Maybe just relativity? I don't know. All those things. We're talking about gravity in one word. So join us next time. Thanks for hanging out for today, and stay safe, stay healthy, and we'll see you next time.